greater.
However, it is a good point that you consider the frictional loss. However, as the nozzle length increases, the airflow will stabilize so that the turbulence inside the nozzle will be decreased, and it will cause a laminar flow. And so, like, if you consider the fact that turbulence will hinder the airflow from the nozzle, don't you think if you increase the nozzle length, it can also be some positive effect for the efficiency as well?
I don't think so, because you see that for a Reynolds number we have the characteristic length of a tube, which is not the length of the tube but the diameter of the tube. So the length will not have no effect, or a very small effect here.
What I would like to prove, what I would like to point out here is that your measurement of Reynolds number was not according to the different nozzle lengths. So it means that if we change the nozzle length, the Reynolds number value will start to change, so that the turbulence is not occurring in the nozzle, so that the airflow can be changed. So, do you agree on the point that the experiment would improve your research?
I have no experiment made because, as I said, the definition of the characteristic length of a nozzle is not the length but the diameter of the nozzle.
But Reynolds number is also proportional to the, what I would like to point out is that there is a velocity term in the Reynolds number. But however, if the nozzle length changes, the velocity of the fluid itself may change too. So did you measure the airflow velocity, the different nozzle lengths as well?
As I pointed out in my formula for the expelled air, the factor here, F, is very small, and also this is very small. So it won't have a big effect on it. The velocity will change a bit, and with this also the Reynolds number, but you see that the Reynolds number is about 40,000. And for a laminar flow, we need a Reynolds number of 2,000. So we need a velocity which is 20 times lower than this velocity, and we cannot reach this.
Yeah, but I think you should have experimentally confirmed that the velocity of the fluid flow will also change according to the nozzle length. So now let's move on to the next topic. So, when you measure the volume pressure, which pressure did you measure? When it is contracted or when it is expanded?
Contract, I've shown you in this measure here. You see the air goes out of the balloon into the pneumatic tank. This experiment is done stepwise, and after each step I measured here the volume, and at the same time the pressure with the sensor attached here.
Yes, but don't you think that long pipe between the pressure sensor and the balloon, it will cause the frictional losses that they emphasize, and it can cause some change in the value of pressure, so that their calculation of the input energy would have been changed.
No, because first of all, this distance is not very long. It's about 5 centimeters in reality. And second, the experiment is done stepwise, and after each step, I waited of about 5 seconds for a stability of the system, and then I measured. So this will have no influence.
So you've mentioned that. So how long was your nozzle? Your nozzle for the car?
One time more, please.
Like the length of your nozzle for the car.
When?
I mean, he has mentioned that the 5 centimeter length is not a great length to cause the frictional losses. But however, applying that same principle to their frictional loss equation, it can also mean that if their nozzle length is not greater than 5 centimeter, they can even neglect the effect of the frictional losses.
The problem here is, as I've said, the experiment is done stepwise, and after each step, the volume flow is cut, and I waited some time, and then the pressure will always be the same in the whole tube here. So I can do not have to consider this frictional losses.
Yeah, so you ignore the frictional losses that you had emphasized before. So now let's move on to the next topic. So the problem asks us to maximize the efficiency. So while your final efficiency, what was the parameter that you considered in the optimization process?
I considered, of course, the type of some of the wheels of the car, the type of the car itself, the balloons, the radius of the nozzle, the length of the nozzle, the radius of, I've said and the mass of the car, of course.
Yes, so, but however, your experimental data only gives the optimal value, the nozzle radius only, so that it means that your optimization will be some kind of like this improvement. So now let's think about another parameter, so to summarize the discussion. discussion, I've mentioned some of the investigated parameters such as the nozzle angle, wheel size, and the nozzle length. They explain that they are not the influential parameters, but they did not show us sufficient historical data to confirm their explanation. So thank you for the great discussion.
Thank you very much.
O pessoal da Coreia, provavelmente, eles tentaram usar demais a teoria deles para fazer um negócio. Tinha muita coisa que eles poderiam ter avaliado.
First thing important, please answer me very shortly. What do you think is the biggest source for the energy loss? So where you lose most of the energy?
It's the non-energy event.
Both then. First thing important, please answer me very shortly. What do you think is the biggest source for the energy loss? So where you lose most of the energy?
It's the non-adiabatic process in the balloon.
Non-adiabatic process, okay? And what's your opinion?
Do Laos, com certeza.
Okay, air resistance. Good, thanks. You mentioned the air drag in the presentation, and as I think if you have this carved balloon, the balloon gets smaller if you travel a certain distance.
Yes.
So can you please tell me how could you calculate the point where the air drag is highest, because you have high velocity and size of the balloon which in fact is. So how would you calculate this?
The biggest
The velocity of the car is great, and also the...
Okay, thanks. And do you think it's the same to maximize efficiency and maximize distance traveled by the car?
I don't think so, since it's possible that even if the car travels over a very distance, but it has a large efficiency.
Yes, for a given amount of energy, initial energy amount, it's the same.
Okay, then another question. Do you think the pedal have a low velocity over a long period of time, or a small velocity over a high velocity over a small period of time?
As I showed, with increasing radius of the nozzle, the distance reaches a limit, so also the velocity of the car will be greater. So with a greater velocity, we have a bigger distance.
Okay, and my question to both, concerning a well-known fact, as called Malins effect, we know that the balloon, if you inflate it more often, loses pressure and elasticity. So do you think it would be better to inflate a balloon more than once and use this balloon would be better for the efficiency?
So the balloon has the greatest elasticity at the first time.
Yes.
So I think to maximize the efficiency, we should use the balloon which has not been inflated before.
Okay, and what's your
I've used the balloon which was inflated about 20 times before, so it can be considered as equal, and with this you change also the energy, so the efficiency won't change here.
Okay. Good.
Nossa, agora ele se ferrou.
Thank you very much, preparation. Task says, build a non-compartment engine using elastic air coil balloons axis, which determine how the distance traveled by the car depends on relevant parameters and which maximize the efficiency of the car. So I think it's important that we have two things to do. First thing, determine the parameters, and second thing, which maximize the efficiency. So here is the outline of the presentation. First, the product gave us a definition of efficiency, told us about relevant parameters, and he gave us possibilities for the optimization. Then we talked about the theory, the motion of the car, and the airflow. And last, experimental observation. We talked about the aerodynamic behavior of the car, about the determination of the rolling friction, and his conclusion. So here are the strong and weak points of the report. He included most important parameters like the air drag and the Reynolds number. He had conducted experiments like the measurement of the air drag, and had a relevant theory concerning his definition of efficiency, which was, in my opinion, not completely correct. But there are some important parameters missing. For example, velocity and acceleration, shape, and initial energy. I also missed PV diagrams for different balloons to see how this works and if every balloon is the same. Then I would have liked a comparison between different car models so that we can see if we have really maximized efficiency. And finally, we didn't include Malins effect, which is, in my opinion, very important for the whole problem. The physical description, elasticity is also missing, like a comparison between the theory and the experiment.
Aquele negócio lá da elasticidade, você não pode usar muitas vezes, mas falou.
Nozzle, the estrogen, of course, Reynolds number,
Acho que é isso.
and at last they talked about discrimination of pressure. So these were answers and questions which the opponent put the reporter in discussion. So the opponent asked, if we would increase the nozzle radius, would you have increased turbulences? The opponent said that he didn't consider this, which is, in my opinion, quite important. Because if we would increase the radius, we would also increase the Reynolds number, which would cause turbulences and energy losses. So the second question was if the reporter thinks that his efficiency definition is correct. And the reporter mentioned, of course, that we think efficiency is defined by the energy you put in the balloon and the output. So this is just partly correct. And the opponent asked about the angle of the nozzle, if this is important. He said not important, and I'm not clear about this now. So the measurement of the airflow, he asked him how he measured it. In my opinion, this is also very important, because by calculating the Reynolds number, he used the velocity of the airstream, and for the velocity he would have measured it. So we got no clear answer. So the strong and weak points of the opponent. He discussed the nozzle, the angle of the nozzle, and the turbulences. He could clearly find the experience lag by measurement of the airstream, and then he discussed about maximization of the efficiency. But he didn't discuss what it depends on the parameters of time, because of course the balloon becomes smaller and smaller by traveling a distance, and the minimization of the ground friction. They also didn't discuss the size of the car, the center of mass. And finally, we asked. So the efficiency and distance, report means, is the same to maximize efficiency, maximize distance. In my opinion, that's not the case. This is correct for the opponent. The Mullins effect, I asked about the Mullins effect because I think it's very important. This is the answer. Thanks, ladies and gentlemen, for reporting.
Thank you very much.
First of all, I want to thank you for the opposition and for the review. I want to clarify something. First of all, you cannot reach laminar flow in the nozzle. Then second, I've varied the shape of the car, and as I said, I've also varied the shape of my balloon and the volume in the balloon, and with this I have also varied the initial energy, but with a greater initial energy you will have normally a smaller efficiency. Then the measurement of the airflow, I've shown you a measurement, and I've done this, as I said, with the video analysis. You saw this movie and a picture out of the video analysis, and because the balloon can be considered as a rotational corpus, you can calculate out of this the volume, and out of this also the volume flow. Then I want to show you this graph. Here, sorry for the German, it's in English it's the angle of the nozzle and the force here in millinewton. And you see that I varied it, and at the beginning the force will be equal and constant, but with a higher angle the force will decrease very fast. And then I have to correct my answer on the air resistance. The air resistance is not at the beginning the highest. It's the highest when the velocity is very high in the area of the car, but I have not determined that point of time because it's not important. Then I have also always took the same balloon, and after extruded so time can be considered as equal, so the Mullins effect does not play a role here. Thank you for your attention.
Thank you very much. And now we have time for jury members to pose their questions.